So we're going to talk about ether synthesis, and so we're first going to talk about the Williamson ether synthesis. And so one of the things you need, of course, is the alcohol, and you need a strong base. And so let's just put B minus here, and we're going to deprotonate the alcohol. The electrons go with the oxygen. And so we're left with what we call an alkoxide. And then we need some electrophile for that alkoxide to attack. So I'll just put it in generic terms here. We'll just do E+. And so this guy goes and attacks the electrophile, which for ether synthesis, that would be some carbon, right? And so we end up with this sort of deal here. Now, strong base. You typically think OH is a strong base. This typically doesn't work for normal alcohols. It's not strong enough because the pKa of an alcohol is roughly 16 and pKa of water is 15.7, so we need a stronger base. One thing you can do is treat this with sodium metal. Sodium metal will deprotonate that to give you the sodium salt of the alkoxide, and then treat this with some carbon that has a good leaving group, right? Typically X here can be something like a halide or a tosyl group, which we'll talk about in a minute, but something that's just a good leaving group, and so we get this attack from the alkoxide onto the carbon, and we form the ether. So, examples of this, which I already mentioned here, are of course halides, right? So halogens, but where I is better than Br and Br is better than Cl. Also, tosyl groups work well for this. Some more examples of this, and there are some things that we're going to end up needing to consider when we look at this Williamson ether synthesis. So here's an example. Let's just make a generic alcohol. So another strong base that you can use is sodium hydride. And if you look at this, right, notice that H minus is going to be a strong base. It's typically referred to as a strong kinetic base, and I'll show you why in just a minute. And then, of course, iodomethane that you see here is a really good electrophile with a good leaving group, right? So what's going to happen is we're going to end up forming our ether. And it's going to go through this sort of generic mechanism that I'm going to show you here, where basically whatever the alcohol is, I'll just replace that, all the stuff around it, with R. And then you have, of course, your sodium hydride. And so what you're going to see is the H minus go over here and pick up the proton off of the oxygen. So now you have your alkoxide. So this is exactly what happened above in the example. And you see that we form H2 gas. It's going to bubble out a solution. So that's going to push us towards the products. And this is one of the reasons why it's referred to as a kinetic base. And then you can see here that we see this iodomethane where the alkoxide attacks the carbon, and we then form our desired ether. notice that this part right here is actually an SN2 reaction. So because of that, there are some factors that we're going to need to consider. And one of the big things here is that, of course, SN2 works best on primary alkyl halides, or primary carbons for that matter. Right? So that means that you cannot use something that is tertiary. Right? So as an example, let me show you this. Here's a tertiary alcohol, or I'm sorry, alkyl halide, and if I treat this with an alkoxide, then what happens here? Well, I don't get substitution because an SN2 reaction doesn't work for tertiary alkyl halides. So instead, what I get is a mixture of E2 products. Right? So this, the way that it's written now, is actually going to favor elimination. Right? So instead of getting the ether that I would want, I'm going to end up getting a mixture of these eliminated products here. Right? So the other thing that you want to consider when you're doing this is to do it in the opposite way, if that's the case. Right? So I can still make this the ether that I want, but I can always do it by making the alcohol the more substituted piece. In other words, make the alcohol the alkoxide on the substituted part. Let the alkyl halide be the less bulky piece because that's the part you're trying to attack via SN2. So if I wanted to do what I have there above, I just need to do it a little bit differently, and I can get the product that I would want. So here I'm converting the tertiary alcohol into the alkoxide and then treating it with iodomethane. That gives me the ether that I want and no elimination. So make sure you look and analyze it so that you don't get elimination instead of the desired ether product that you're looking for. Now we can also make ethers using phenols, and there is something that you want to consider here. In particular, we're looking at some pKa values. So pKa values of phenols is less than the pKa value of alcohols, right? So we have a lower value there. And so what that means is that we can actually change the base that we use a little bit. So remember, phenols have pKa's of around 10, whereas alcohols have pKa's of around 16, right? So this actually changes things for us quite a bit and allows us to use bases such as sodium hydroxide. So keep in mind, only when you're using phenols can you do this. If you have a regular alcohol, you really can't use sodium hydroxide. But why is the pKa of a phenol lower? The answer to that is, of course, one of the answers that we get commonly in organic, and that is due to resonance stabilization of the phenoxide conjugate base, right? So here's an example. Here is our phenoxide. And I can draw a resonance structure by kicking these electrons in and moving this out. And I won't bore you with the whole deal, but you can imagine that we can go all the way around the ring. And so the negative charge that's on the oxygen is actually stabilized by moving it, or its ability to move via resonance all the way around the ring. So this dramatically decreases our pKa, and this allows us to use a little bit of a weaker base. So we can draw in some examples now, or I'll rather one. And so here I'm going to treat this with sodium hydroxide, and then that's going to give me the phenoxide, right, which is what we call the negative O on the phenol, and then you can easily form your ether in the same mechanism as was previously. There is a factor to notice here on this part, and that is that you cannot do this in the reverse, right? So for instance, you cannot take an alcohol treat this with a base, and then try to make the ether using this type of aryl halide. This reaction doesn't work, right? If you want to make the phenolic ether, then you're going to need to go from the direction that was shown above. Now, we can also make ethers using what we call alkoxymercuration. And of course, this is something that we can remember back from Organic 1. So if we remember here, what were the necessary ingredients here for alkoxymercuration? Well, we need an alkyl, or we need a double bond, right, an alkene. And then we're going to need to treat this with mercury acetate. And of course, we're going to use water. And in this case, water would be our nucleophile. And then we finish everything up using, that should be sodium borohydride at the bottom, not water, and number 2. So we're going to use sodium borohydride there, right? And so now we can do the same thing. And remember, this is Markovnikov. And if you need to go back and remember how this works, please do. Please review this from Organic 1. But if we change the water ingredient, which should not be on number 2 above, right, that should be sodium borohydride. If we change that to mercury acetate and then an alcohol, so let's just use methanol, and then add sodium borohydride, we see that we can in fact get Markovnikov addition of the alcohol, which forms the ether that we need, right? So we can still use things that we learn in Organic 1 to accomplish the necessary synthesis of ethers that we see here. Again, it's the same pathway. Nothing really is different. It's just that we're just using an alcohol. So it's the same thing as you were to use alcohol synthesis with water. One thing to note, though, is that tertiary alcohols do not work for this.